Hello everyone and welcome back. So in this video we'll be looking at some of the applications of Gauss's law of electrostatics that we looked at in the previous video. So these applications include finding an electric field due to an infinitely long uniformly charged wire. Then we'll look at the electric field due to a uniformly charged and infinitely large plane sheet. And then we'll look at the electric field due to a uniformly charged spherical shell. So these are the three things that we'll be looking at. And in addition to that, I will also do a derivation for this case for the electric field that is created due to an infinitely long uniformly charged wire using Coulomb's law to just contrast and compare both laws and see just how the symmetry arguments due to Gauss's law massively simplify a lot of cases. But in cases where there is no integration or when there's no symmetry involved, we'll usually use Coulomb's law because there is no other choice for us. Alright, so let's begin with the first case. I'll begin with drawing an infinitely long wire. Of course, drawing an infinitely long wire is not really practical. So what I'll do is I'll just draw arrows over here to indicate the fact that this extends all the way in both cases. Let me just denote that this is the first case. So an obvious problem that occurs over here is the fact that we are dealing with an infinitely long wire, so we are also dealing with an infinitely long charge. So infinitely large amount of charge. So how do we actually, get something finite that we can work with? So in cases such as these, what we do is we define a form of density. In the case of the wire, what we'll do is we'll define a linear charge density, which is denoted by lambda, and we'll denote this as q, that is the total amount of charge on the wire, divided by the total length of the wire. And since we could say that both of these quantities are infinite, we get a finite value. Or if you don't like this idea, this is also equivalent to defining this as dq by dl, that is an infinitesimal amount of charge contained in some element over here, that is some element dl over here, and we are going to call this amount of charge over here dq. So this is how we overcome the problem of infinities occurring and things like that. So now we'll actually begin with defining a Gaussian surface, because that's important in problems like these. We need to identify a surface that's symmetrical, that has some symmetry with respect to this wire, so that we can take the electric field out of the Gauss's law equation, and then we can sort of simplify it. Because if we don't find any form of symmetry, then it's not very useful applying Gauss's law. I think it's just better to proceed with Coulomb's law in cases like that. So the surface of symmetry in this case is actually going to be a cylinder. Is there a shape that, I don't think there's a shape that will be very useful over here. So let me just draw a sphere over here. And another, not a sphere, or rather a circle. And this is the cylinder that we're talking about over here. So you can sort of imagine the wire threading through the cylinder. And then there's a hypothetical cylinder. Of course, this is not actually a solid object that we're talking about. So this is a hypothetical cylinder, and we want to find the electric field on this surface over here. So again, now what we're going to do is we're going to apply a symmetry argument. We're going to say that this wire is infinitely long. So there is no particular point on this wire that is different from, say, this or this point. So all the points on this wire are identical. Therefore, the electric field in front of these points should also be identical. And that arrangement actually involves the electric field lines going like this. That is, they have to be perpendicularly outwards to the wire. So now some of you might be thinking that even this looks like a very symmetrical form of arrangement, right? I mean, if the electric field lines were like this, even then they would be symmetrical with respect to these charges over here. But in this case, you need to remember that these are all positive charges over here. And we know that electric field lines are coming out of positive charges. So even in over here, they'd be like this if in this hypothetical model. And so that will violate the fact that electric field lines are always outwards from charges, because that would imply that this is perpendicular to the charge over here, which is not possible. So keeping these things in mind, we're going to now apply Gauss's law. So first we're just going to state it, that is a closed integral. And of course, this is actually denoting the electric flux is equal to Q enclosed by epsilon naught. Now over here, you do need to note that Q enclosed is not infinite because the cylinder that we've chosen over here is of finite volume. So we're only talking about the charge enclosed in, suppose, this region over here, from over here to over here. And so that value actually is finite. And so now we'll try and find what this value over here is. So finding this value over here actually involves breaking down this surface into three separate regions. So this is suppose region 1, this is region 2, and this region 2 is actually the curved surface area. And this is region 3, that is the sort of the base of the cylinder. So 1 and 3 are the two ends, and number 2 is actually the curved surface area. So when we are trying to find out the E dot ds for this region, so we need to keep in mind that the area vector is actually perpendicularly outwards, right? It's going to come out of this area or this sort of the base of the cylinder over here, whereas the electric field, as we have established, is actually perpendicular over here. So you can clearly see that E dot ds will be equal to 0 because E is perpendicular to ds. So for E dot ds for surface 1 and surface 3, because that same thing applies over here, because A will be over here in this direction and E will be over here in this direction, will be equal to 0. But for surface 2, this is not the case because area vector is along also this direction, and so is the electric field. So they are parallel, and so E dot ds will just be equal to E ds. So let me just write that down. This is equivalent to basically for surface 1, or I can remove the sign over here because it's not a closed integral anymore. This is equal to, I wrote it again. This is equal to the integral for the surface 1, or my bad, surface 2. Surface 2 E ds is equal to Q enclosed by epsilon naught. Now what is this Q enclosed over here? We can further write this actually over as lambda, that is the charge density, times the length over here. That is the length that we're talking about. We can call this, suppose, say length L of sorts. And we can consider this to be a cylinder of radius, say, R. I realize that this diagram has become very messy. Yeah, so this is a cylinder of radius R and length L that we've considered over here. So the curved surface area of a cylinder is actually equal to 2 pi RL. So when this can further be written as E times 2 pi RL is equal to, oh, I forgot the epsilon naught over here, is equal to lambda L by epsilon naught. So this and this get cuts, and so you can see that E is actually equal to lambda by 2 pi epsilon naught R. So it's actually independent of the length of the cylinder that you consider. Moreover, it's inversely proportional to the radius. So upon contrasting this with the electric field due to a point charge, you'll actually find that this is only inversely proportional to R, whereas due to a point charge, the field is inversely proportional to the radius. It's an inverse square law. Moreover, even though we had an infinite amount of charge, you'll find that the electric field is actually a finite value. So that's also something that's pretty interesting. And so you can form various conclusions from this result, and I'll leave that for you to do on your own. And now I'll move on to an alternative derivation, that is using Coulomb's law, just to show you how much harder it can get, or how much more complicated it can get. And so this was pretty simple. All we had to do was actually form our surface properly with some amount of symmetry, and we were able to find the answer quite easily. But now let's talk about the Coulomb's law. So in this case as well, I'm going to take the help of an infinitely long wire over here. And now I'm going to find the electric field at a distance, say, A from the wire. So suppose I have this over here. Let me just draw this over here. So this is some distance A. And I want to find out what the magnitude of the electric field is at this point. So I'm going to call this distance A. And the electric field is what we have to find. So suppose we have got an infinitesimal element dl over here somewhat. So this is an infinitesimal element dl and it has charge dq, and we can write lambda as dq by dl. And of course, since I said that this is a uniformly charged wire, lambda is actually constant, and so this value is the same for all elements dl across the wire. And I'm going to say that this is at a length, suppose we can call this L. So this is at a length L from this point over here. That's an arbitrary point that we have chosen. So it's going to be at a distance R, and this distance is going to be R from this point over here. So we can write R is equal to root of L square plus A square. So from this is what we're going to move forward with. Then we can write dE, that is the electric field due to this element over here, that can be written as dq by 1 by 4 pi epsilon naught. This is from Coulomb's law, and R square. So this can further be written as dq by, then again we have to take care of this constant, and this will be equal to L square plus A square. But we can't simply integrate this because this is actually in a vector quantity. This has a direction, right? It's actually directed in this direction over here. So we have to find some or the other, or have to make some or the other conclusion, and then you can move further. So I wouldn't say that this is a symmetry argument, but it is somewhat similar to what we did in the previous case. So you have to remember that for each element dq, we have another element dq that is at the same distance L, and it's creating an electric field in this direction, right? So we have electric field in this direction and this direction. So what actually occurs is that when you take all the pairs of elements in this direction and in that direction, the horizontal component that is created by, say, charge 1 over here is cancelled by this charge 2, because you have to remember that each of these acts also create their components like this and like this. So the horizontal components are simply cancelled out like this. So what you're left with is a net vertical field that somewhat points like this. So we only need to consider the vertical component of each electric field while we do the integration. So that is exactly what we're going to do over here. So what we're going to write next is the thing that we actually care about is dE sine theta, where theta is this angle over here. So you can see that sine theta is equal to A by R. So I can further write this as dE sine theta, and that is equal to dq by 4 pi epsilon naught into L square plus A square times the sine theta is actually equal to A by R, which I can write as root of L square plus R square. So A by root of L square plus R square. L square plus A square, my bad. L square plus A square. And dq can be written as lambda dl. So this can then be written as A by 4 pi epsilon naught into L square plus A square raised to 3 by 2. And this is the actual expression that we have to integrate. And as you can see, this isn't a very elementary integral. You'll have to rely on a few trigonometric substitutions. So we'll do that now. Well, luckily for us, we don't need to go very far for our trigonometric substitution. All we need to do is observe the figure in front of us. So over here, we can see that tan theta is actually equal to A by L, right? So let me just write that. So tan theta is equal to A by L. So L is actually equal to A cot theta. Therefore, we can write dl upon differentiating the right hand side. We can write that as minus A cosec square theta d theta. And so we can now substitute this in this equation. So this can be written as lambda dl into, oh wait, I have to substitute dl, or my bad. So this can be written as lambda times minus A cosec square theta d theta, and Then we write a as well, a by 4 pi epsilon naught. And over here we'll take a cube common, and then we can write this as 1 plus cot square theta whole raised to 3 by 2. Now this is only the differential form. I actually have to write it as an integral, right? This is only dE sine theta. Alright, so the limits for this integral can be found by looking at this value over here, right? We want an integral that goes from, or value that goes from, say, minus infinity when L is equal to minus infinity, and then it ranges to, say, L is equal to plus infinity. We want the values for that. So when it's minus infinity, we see that tan theta is 0, and when it's plus infinity also, tan theta is again 0. So that might not tell you very much, but you do know that this actually implies that tan theta is a very small negative value. So that means that our integral has to go from minus pi to 0. So because when it's a very small positive value, tan theta is approximately equal to theta, and that means theta is approximately equal to 0. So our limits over here are actually going to be, say, from minus pi to 0, and I'm going to sort of erase this over here so I can write all the constants outside. This is going to be equal to lambda by 4 pi epsilon naught, and there's now going to be an a square in the denominator. Oh, no, there's only going to be an a, my bad. Just one a, there's no a square. And so this is actually further simplified by writing cosec square theta d theta, and denominator you'll actually get, this is 1 plus cot square theta, this is nothing but cosec square theta, and since it's a cube, we'll get a cosec cube theta in the denominator. This is actually cosec cube theta, and so we can simply cut, and we'll only have a cosec theta in the denominator. So that's actually equal to sine theta. So this integral was luckily simplified in this manner. So we can write this as sine theta d theta, and this is nothing but minus cos theta. So we can write the limits over here. Oh, the limits are actually 0 and minus pi, but it doesn't matter because either way you'll get cos of pi or minus phi is still minus 1. And of course there's actually a negative sign over here. If you'll notice, there was a negative sign. So then when I write the whole thing, I can write this as minus lambda by 4 pi epsilon naught a times, that's first we're going to write minus cos 0, so that's minus 1 minus of minus cos pi, so that will be plus cos pi, so I can simply write that as minus 1 again, minus 1, and so we can cut. So this will actually turn out to be, ta-da, it's going to be the same thing because, well, that has to happen. So we get the same result for the electric field using Coulomb's law, but the derivation or the process was much longer, as you can see. So Gauss's law has the ability to simplify a lot of problems in physics, most particularly when you're trying to find the magnitude of electric field and similar things. But it requires a lot of symmetry. So we didn't have to apply Coulomb's law in such a situation because there was symmetry that we could exploit. But when there is no symmetry, then we have no other option but to proceed with Coulomb's law. And I actually did plan to make the other two applications in this video as well, but I think the video will become a bit too long if I do proceed with that. So I'll make the other two applications, that is just the Gauss's law applications and not the Coulomb's law view of it, in the next video. So I think that'll be it, and thanks for watching.